Deep space, beyond the orbit of Neptune, Pioneer 10 drifts, a silent speck against the black velvet of the cosmos. Its mission complete, it sails on, utterly alone. The navigation data arrives at JPL, clean and precise. Yet something is subtly wrong. The Doppler shift from the spacecraft's radio signal indicates it's slowing faster than expected. Not by much, a fraction of a centimeter per second squared, but it's there. A tiny, persistent tug towards the sun. Impossible. The anomaly appears in the numbers, cold and undeniable, like a fingerprint on a frozen window. For years, astronomers chase ghosts. Theorists propose new physics, modified gravity, unknown forces bending space. The anomaly persists. It becomes a puzzle etched into the fabric of deep space exploration. Teams dissect telemetry, hunt for errors in the tracking stations, question every instrument. The answer remains hidden in the silence between the stars. Then in 2011, a quiet breakthrough. Scientists recover decades-old telemetry data. They painstakingly reconstruct the spacecraft's thermal emissions. They map the heat radiating from the RTGs and electronics, minute by minute, across the vast distance. The design, they see, caused more heat to radiate backwards than forwards. The spacecraft's own warmth, pushing against its motion like a gentle breeze. The anisotropic radiation is the culprit. A tiny recoil force, imperceptible in daily life, adds up over billions of kilometers. It explains the exact deceleration measured. The numbers align perfectly. No new physics needed. The decades-long mystery dissolves into the mundane reality of heat dissipation in the vacuum of space. The Pioneer spacecraft slowed down because they were warm. The Doppler shift data held steady. For 2 decades, the anomaly persisted in the navigation logs, a consistent, minuscule deceleration, not a fluke, not gravity's pull, a tiny, persistent tug towards the sun. The numbers were precise, 8.7 times 10 to the minus 10 meters per second squared, measured across billions of kilometers. The spacecraft weren't just slowing, they were betraying a secret they carried within their own warm shells. Early theories scrambled. Could gravity itself be different out here? Modified laws of physics, unseen forces bending spacetime, or perhaps a faint interstellar breeze, a cosmic wind pushing back. Some even suggested the spacecraft were emitting a subtle, unnatural energy field. Each idea fit the data imperfectly. Each required rewriting established physics, but no evidence ever supported these leaps. The anomaly remained stubbornly alone in the cold. The thermal explanation emerged from careful reconstruction. Engineers mapped the spacecraft's heat signature using recovered telemetry. The RTGs glowed steadily, radiating warmth. Electronics hummed faintly. The design, built for deep space, directed this heat unevenly. More infrared photons streamed from the back, away from the sun. Each photon carried momentum. As they shot backward, the craft nudged forward a tiny recoil. The direction mattered. Heat radiating backward pushed the Pioneer forward, slowing its outward escape. The math aligned perfectly with the measured deceleration. After years of cross-checking, multiple teams confirmed the solution. The thermal recoil force, meticulously calculated, accounted for every nanometer of the anomaly. The final papers left no gap. The acceleration vanished once heat distribution was modeled correctly. The Pioneer weren't defying physics. They were simply radiating heat according to their design. The answer wasn't hidden in the stars. It was etched in the thermal patterns of their own power systems, a quiet truth lost in the vast silence for 30 years. The first theory to collapse, modified gravity. Astronomers gathered in dimly lit rooms tracing equations on chalkboards. They imagined space itself resisting escape, a cosmic drag. But the anomaly pointed relentlessly sunward, a constant nudge. Gravity models predicted varying effects across the solar system. They couldn't match the Pioneer's steady, tiny deceleration. The math was wrong. It demanded a force tied to the spacecraft's own structure, not the fabric of space. A single, unexplained number refused to fit. Another theory faltered on direction. Some proposed spin-induced effects, a wobble in the craft's gyroscopic motion. Yet the Pioneer's spin was stable, measured in telemetry down to the millisecond. The deceleration followed the craft's physical orientation, back to front, away from the sun. Heat signatures mapped precisely onto the hardware, RTGs glowing steadily at the rear, electronics humming faintly in uneven clusters. The direction of the push was fixed by the design, not by motion. The hypothesis collapsed under the weight of the physical evidence. The final proof arrived in thermal maps reconstructed from decades-old telemetry. Engineers painstakingly decoded fragmented data from frozen tapes. They mapped every watt of heat radiating from the RTGs, the electronics, the very hull. Infrared photons streamed unevenly, concentrated from the rear, away from the sun. Each photon carried momentum. As they shot backward, the craft nudged forward, a recoil too small to feel but calculable. The math aligned perfectly. 7x10 ms2, the exact deceleration measured over 30 years. No new physics needed, only the spacecraft's own warmth radiating into the void. Multiple teams cross-validated. The 2012 papers, built on meticulous thermal modeling, confirmed the recoil force accounted for every nanometer of the anomaly. The anomaly vanished when heat distribution was modeled correctly. It was a matter of precise engineering, not cosmic mystery. The Pioneer weren't defying physics. They were simply radiating heat according to their design, a truth obscured by the vast silence of deep space for 30 years. The answer wasn't hidden in the stars. It was etched in the quiet hum of their power systems, finally understood. What other quiet truths are we missing?